My name is John Hedengren, and I appreciate this opportunity to share some information about control and optimization using Python Gekko, a package that we developed in 2017, and talk about some of the extensions. I'm presenting with LeGrand Gunnell at the American Control Conference, and this is a preview of some of the things that we're going to cover in the tutorial session for Gekko. So first of all, I'll cover current trends, Gekko applications, some tutorials as well. We'll do energy dispatch, system identification, temperature control lab, model predictive control, Gaussian process regression, optimization. Then we'll also create Gekko applications with generative AI. And I'll show a demonstration of that as well. Currently, there are about 200,000 or a little more installations per month of the Gekko optimization suite. Some of the highlights are that we have a new interface to Pyomo, and also a recent interface to Ample as well, and then also TensorFlow, scikit-learn, and GPFlow as well. To get started with Gekko, you just do pip install Gekko, and you can solve problems with differential algebraic equations, nonlinear programming, mixed integer nonlinear programming, partial differential equations, linear programming, quadratic programming, mixed integer linear, and doing applications with machine learning, model predictive control, moving horizon estimation, real-time optimization, and regression. So with all of these, I'll show some demonstration applications, be able to go through applications of Gekko. Now, first of all, let's just talk about programming language popularity. You can see in 2009, 2010, still Java is very popular, PHP as well as a programming language for the World Wide Web. And you can see Python emerging now, taking a great share of not only scientific computing, but also many other types of computing industries using Python now. So let's talk about open source motivation, the reason for developing in a package that's open source versus commercial and proprietary. So first of all, the main thing with open source is developer mindshare. You get a community of developers that get behind a project, and sometimes they require a sponsoring agency, such as the Department of Energy or National Science Foundation, or a business as well that uses it and wants to share the development costs. Also, there's transparency of results and building this community of developers. So the important things for the development side are developer mindshare, community, and then also from the user side, you want to emphasize things like ease of use, assistance, and features. Help those who are developing in this environment. And I'll show some exciting developments with generative AI and Gekko. So some of the things that you want to pay attention to when looking at open source packages and adopting those is the community engagement. So how engaged is the community, not only from the developer side, but from the user side as well. Looking at installation rate, Q&A forums, citations. When was the latest release? Does it look like it's actively developed? Documentation. What OS support is there? Ease of installation. And then how easily can you extend it and scale it? So I'll talk about a couple applications with Gekko. This is one, a high altitude, long endurance aircraft, and using model predictive control to control the motion of the aircraft in order to be able to capture the most sun. Now this is at winter solstice, so the sun is low in the sky, and the goal is to try to remain in the air for 24 hours. With solar power covered, these solar panels that cover the wings, and the rotors that use about 1,500 watts of energy. Let me go back to that. Okay, so we have this repository here that shows an example of using Gekko Optimization Suite to perform this energy, which is really like a microgrid system. And it did some surprising things when it figured out how to fly most efficiently to get up to that 24-hour mark. It would climb when it filled up the battery. Okay, so when the battery was full, it would climb, it would preserve more energy in elevation, but then it would also fly in a way, okay, these kidney bean shaped flights, to be able to bank into the sun and be able to capture more energy that way. So it did some things that were not necessarily intuitive from looking at the problem initially, but then after exploring the optimization and the solution, it made intuitive sense. And so the main point here is that Gekko is used for a fairly sophisticated system, microgrid energy system, to be able to optimize the flight path of this UAV. You also have other applications like drilling automation, where there are very sophisticated models. Some of these models are hundreds of thousands of differential equations, very detailed. And the idea is, how can we use these detailed simulators in an industry and be able to apply those in control applications? And so one of the challenges is using surrogate models and be able to develop those from the more sophisticated models and be able to use those in real-time control applications. And so in this case, we used a surrogate model with 3 ODEs to be able to model the more complicated process and be able to control the drilling application, be able to detect and mitigate gas influx or kicks into the wellbore. So it's just another application using Gekko with these more sophisticated models to be able to control a process. Now we'll give some examples and go through a tutorial here where you can solve some of these problems as well. We typically do this with the simple benchmark problems to be able to show, for example, this is a demand production with storage and retrieval, and a very simple differential and algebraic equation system with an objective as well. It's also subject to additional equality and inequality constraints. And you can see some of the results here where the energy is stored and then recovered. Okay, and then you can also see the storage here, and you can see the demand and production as well. So there's one benchmark problem where we're going to solve that with Gekko, just as a benchmark that's typical of this energy dispatch and storage and retrieval. Here's another one about cogeneration. This is also an issue where you might want to be producing electricity and heat for a process. So you put the electricity generation close to the heat demanding processes, and then you can use both electricity and the heat that's produced as a waste product. Okay, so you have certain demands, not just one demand in this case. Okay, but you're going to have the first one and then a second one as well. And the ramp rate is controlled to be able to meet both demands. So this is a very simple application of Gekko, and it shows some of the capabilities of being able to solve these types of problems. In this case, it's an offline once optimization versus model predictive control where we iterate in a certain cycle time. So I'm just going to visit this URL right here, and it gives more information on the energy system benchmark problems. There's also a video there that goes into more detail. But as part of this tutorial session, we're going to go through and solve some of these problems. So for example, here's the first one that I mentioned, just a production and demand ramp rate. Okay, and here's our second one, the cogeneration problem, and then you can see the source. Okay, and then let me get down to the one with constant production and storage. All right, and so if we come down here to the source, then we can copy this, get code, and put that into a Jupyter notebook. So I'll open up a Jupyter notebook. Okay, and I will go here and do load, paste in the URL, and then it will copy in the source code. I think it will copy in the source code. Okay, didn't do that. Let me go ahead and try this again. All right, and I can just copy it in as well. All right, and then click, just go ahead and run it and have it solve, and here are the results. Okay, so I encourage you to go through some of these tutorials, be able to run the code, solve it, and be able to explore some of these energy benchmark optimization problems with Gekko. Okay, so I'm going to leave this one, leave that one, and close this window to get back to the presentation. Okay, so now we're on the next one, different types of models. So those last models are more physics-based models where you know the equations and you're going to write down differential and algebraic equations to model the system. And those can be physics-based. So those would be something like a physics-based model. Okay, but you could also have things like in dynamic modeling, maybe something like an ARX or FIR model that are popular for industrial process control, where you don't necessarily know the physics of the system, but you're going to identify it from data. Now, there are many other types of models as well. You can linearize a physics-based model to get a linearized physics-based model. And on this side are the linear models, and on this side are the nonlinear models. So you've got different types of models like physics-informed neural networks, hybrid models, long short-term memory models, transformers. On the linear side, you have state space models, you have first order plus dead time models, transfer functions, and other types of linear identified models. Okay, so one of the add-ons to Gekko, this is a platform for system identification, and this is the Seek workbench. I'll just mention it a little bit. You can run this through Seek, or you can run this through a Jupyter notebook as well. But it helps you identify some of the models that are important for control applications or building soft sensors or inferentials. So if you come to this link right here, you'll see the Seek identification package. I'll give a little bit of a demonstration of that as well. You can also do pip install seek-sysid. Okay, so here's a system identification interface. This is either run through a Jupyter notebook or with Seek, and it connects to this workbench to be able to retrieve data. Okay, there's different types of models that can be used here. You've got time series models, you have subspace, identification, neural network, and also transfer function. And we're looking to add additional ones like transformers to this. Okay, so here's an example where you select the manipulated variables, the inputs to the model, and then the things that you're trying to predict, the different type of model structure, and then you click identify. It identifies the model. You also have a validation button, and you can push the model back to the Seek workbench, where then you can work with it with additional data in training or validation. Also share a little bit about this Model Predictive Control course. Now this is the temperature control lab. We've distributed or built about 12,000 of these. They're used commonly in university courses or by industry professionals to be able to learn control and topics like machine learning, data science, but also advanced control topics as well, like model predictive control. So So I'll just come to this dynamic optimization course where scroll down on the side to the Arduino lab, and this shows kind of a complete process of going from modeling with digital twin, estimation, and then predictive control with these different labs here. I'll mention in particular lab F, which is linear model predictive control, where you're going to identify the model from one of these statistical approaches, such as an ARX model, and then be able to control the temperature control lab, so the little physical device. So here is an example of the different set points for the temperature. You can see on the top and on the middle one, those are the temperature 1 and temperature 2. And you've got a region where you're trying to control the temperature. Now you can see also on the bottom part, those are the heater values. And the vertical line is the current time. And it shows the predicted control moves. Then after those control moves are made, you can see that line becomes static. So here's the sample code for that, the identification with ARX. And then you can see the source code for that, for identifying with system identification. Or you could use the seek sysid package to be able to do that graphically as well. Okay, and then after that, you create a plot and then start running the predictive controller. And then after it's done, it saves a figure and closes the application. Okay, so that's a little bit about linear model predictive control using Gekko with an ARX model. Now I'll mention here on the right, here is a flowchart based on, if you have data, you might have something like this ARX model or a time series state space model, okay, if it's linear. And if it's nonlinear, you might have a machine learned model or do something like reinforcement learning or estimation of one of these nonlinear models that were shown and do nonlinear model predictive control instead. So different routes here. If you don't have data, you might take a physics-based, a differential algebraic equation model, partial or ordinary differential equations, maybe do moving horizon estimation with that, and then nonlinear model predictive control, or linearize it and then come back to a linear approach like a state space model. Okay, so this is the course. It talks about designing the application, curating the data, predicting, estimating or aligning, and then controlling. So a little bit more about the temperature control lab. There are 2 actuators and 2 sensors, and you've got heaters that are next to each other, so there's a little bit of coupling. So as you increase the heater value on side 1, you're going to see a slight temperature increase on side 2. And so it's a multivariate problem where the heater 1 and heater 2 affect each other, okay, where you get a larger response with the corresponding heater, but you also feel the heater next to it as well. So you've got heater 2, okay, and temperature 2 here. And then on this side, you have heater 1 and temperature 1 as well. Okay, so that was the linear model predictive control with the ARX model. There are other labs there that show how to use machine learned models to do the control applications, as well as these linear, statistically identified, or you could also have a physics-based approach to this temperature control lab, as is shown here. Okay, so let's talk about kind of this combination of physics-based and data-driven control and optimization. So in Gekko, one of the objectives of this is to have a platform where you can mix and match different types of models. There may be a discrete state space, a continuous state space, something like a neural network model, maybe a support vector regressor, Gaussian processes model. You can mix and match all of these into this single environment, solve it with the APOpt or BPOpt or IPOpt solvers, or you can also interface to Ample or Pyomo and be able to access things like Cplex, Gurobi. Depending on the type of application that you're trying to solve, you could use a specialized solver for that application. Talk a little bit about an application in physics-informed, data-driven modeling. This is for Pacific Northwest National Laboratory, who's supporting the Hanford nuclear waste cleanup through vitrification of this low activity or high level waste, and be able to maximize the waste loading into that glass to be able to minimize the number of canisters that are created, be able to speed up processing of the nuclear waste. And so one of the key things about this is be able to create these models that can then be used in optimization. So models that also include uncertainty within the prediction, and be able to use that uncertainty to be able to not only optimize the deterministic value, but also optimize under uncertainty to give a solution that is certain within a certain confidence region that it will be able to meet the constraints of the process. And so this is a project that Legrand Gunnell has been working on, and there's a publication here with additional information. And this has really fueled some of the activities to be able to interface these machine learned models into the Gekko platform to be able to perform this optimization with gradient-based optimizers. So that speeds up the optimization significantly over something like a Monte Carlo search or other types of particle-based methods for optimization, or genetic algorithms or others. Okay, so let's just take a look at this. We're going to go into this just a little bit more. Optimization with uncertainty quantification, be able to use the uncertainty within the optimization, and we're going to go into this just a little bit more. There's a TCLab notebook that's going to be able to help us go through some of these exercises together. Okay, so what I have here, if you follow this link, it'll take you to the source code, but let me explain first before we go into this just what we're going to be doing. Okay, so we have some randomly generated data that comes from a source function. So that's the true function. We're going to sample from that with a little bit more of a cluster right here in one area, and then also less standard deviation of that measurement. So it's just more accurate right in that area. Let's say we want to develop a model from this and be able to optimize to find the minimum. Okay, that might be a minimum cost or other type of parameter that's important to us to be able to optimize. So we're going to develop a Gaussian process regression model that is shown here with this green dashed line. That's going to be the expected value from the GPR model. But with that, we also get a measure of uncertainty. GPR is a non-parametric modeling method that also produces uncertainty. And this dashed line below shows the uncertainty of that prediction. Now you can see in this area where there's more data, we have lower uncertainty. And so maybe in an application, you not only want to find the deterministic value of the optimal minimum, but you also want to find a solution that's maybe more certain. Okay, so if we want to optimize the uncertainty, that's going to be this black dot. Okay, that's going to be the solution for that. Now, if we want to optimize just based on the minimum, that's going to be our red square. Maybe there's a compromise between those two. We want to find the minimum, but if there's something more certain nearby, we'd like to choose that instead. Okay, and so that's going to be this blue square right here. Okay, the combined optimization, maybe a weighted sum, is the objective between the deterministic value and the uncertainty as well. Okay, so let's go ahead and open up this link. And if you come here, you're going to see a Google Colab link for us to be able to go through these together. Okay, so here is Google Colab. You can also just download the Jupyter Notebook and run it yourself. Okay, so I'm just going to select Run All just for the sake of time here. But I encourage you to go through each of these and be able to see how it installs. And then we're going to generate the source data as our next step. We'll split the data into training and test sets. Next, we'll do the Gaussian process regressor. So we're going to train the model. Okay, we'll fit it. And then we have a model visualization as well. We'll be able to show how that works. Okay, so let me see how this is going. Okay, so it's installing Gekko. Okay, that was not installed by default, so it installs it here within this Google Colab notebook. Okay, you can see the data that was generated. It's split. All right, here's our R squared for the GPR regressor. Okay, and then it shows our uncertainty as well. There's our trained model, as well as the source function and the data. Okay, if we just want to optimize just the expected value, we're going to minimize y, and it shows us how to optimize with that GPR model. Now let's say we want to optimize the standard deviation instead, the uncertainty. We can also minimize that instead. And there you can see the solve. It gave us a different solution close by. All right, but now we want to minimize maybe a weighted sum of the two, y plus 50 times the standard deviation, and then optimize that instead. Okay, let's go ahead and visualize the results. As we showed before, we want to try to find something that's the blue triangle. It's a compromise between the uncertainty and the minimum. Okay, I'll go ahead and close this, and we'll get back here. So the final thing I want to touch on is a little bit about finding support for your application. I've showcased some applications here, but chances are the thing that you're interested in is different than anything I've shown. And so one of the biggest obstacles to getting started is just getting that first application or examples, or I've got a bug in my code, how do I get past that? So writing the initial application can be fast, but digging in and kind of iteratively going through finding the correct solution for the problem can be a challenging process, especially when you're not familiar with the syntax or other things. So generated this Gekko support chatbot. It's through GPT-4. It's freely available, but it's trained on hundreds of Gekko questions and answers. So here's an example optimization problem in Python Gekko, and it generates it and then explains the solution. So it's using retrieval augmented generation with the GPT-4 model to be able to give these results. Here's another example built into Gekko from Gekko import support. You create a new agent, and then you can ask that agent something like create an example optimization with Python Gekko. So you don't have to leave the Jupyter Notebook environment in order to be able to get support for your application. And here you can see the problem is solved. If I put display equals false, it doesn't show the solver output, and I can solve locally as well. All right, so here's a dynamic simulation. I'll create a dynamic simulation just based off an image. So I've just uploaded an image of my process, and I want to be able to generate a simulation of this. It's going to generate a simulation of this 2-tank system with a pump and a reservoir. Now this is just from the image that you see on the right there, and there's a QR code to take you to that. You can try it out as well. Just go ahead and upload that image and ask it to develop a Gekko simulation of that system. Okay, we also have dynamic simulation of this continuously stirred tank reactor. Assume liquid full and first order kinetics. Use Python Gekko for the simulation. So it lists the assumptions. It shows the equations it's going to use with species and energy balances. It defines some constants that you could change, and then the differential equations for the simulation as well. So it does a fairly good job just based off that image. A short description of what I'm looking at for it to develop. You could also create a model predictive control application for a manufacturing process that produces polyethylene in a gas phase reactor. Okay, the MVs are catalyst flow and hydrogen ratio to monomer. The CVs, or controlled variables, are production rate and melt index of the polymer. So it'll go through, and in this case, it just develops a linear model, okay, and then the visualization of that with model predictive control, and it goes through the steps it would take to be able to develop this reactor model. You'd likely need to go back and change that, or maybe ask it to give a more sophisticated model. Let's say you want to give more of a physics-based approach on this fluidized bed reactor, for example. Okay, so those are just some examples of using Gekko, this chatbot, to be able to create your application or find, debugging help, resources with this. Also share with you, let me go. I'll just exit out of this. Okay. The other thing I want to just share with you is, there's other resources as well. In addition to, the ChatGPT, there's also read the docs. Okay, so I'm going to go to the documentation. It just gives a little bit of a quick start guide and, building models, modes, and others for those that would like to go through this. Also, here's the support with the information about using the support agent in your script directly, or going to this GPT-4 support as well. Okay, so a couple different options for getting support. And then also mention there's also through Stack Overflow, if those question answers, maybe the chatbot isn't doing it for you, there's some other thing that's going wrong with it. We have an active community where people are asking questions and getting answers, almost 900 questions at this point, with great community engagement. So I encourage you to ask questions there as well. It's kind of like use these chatbots, use things that can get you an answer quickly, help you develop the applications. But if you really get stuck and need that community support, this is also available. Okay, well, thank you for your attention. I appreciate the opportunity to present and give this tutorial session, and look forward to your questions as well.